Our next speaker is Dr. Kenrick Nelson, and we are going to be talking about a specific approach for validating a metric. Kenrick and I both come from an information theoretic background, and I will let him explain the significance of what he is doing.
Okay, so I'm going to talk about a little bit different approach to risk metrics, and specifically in how we would do assessment on inferences that we would make if we're trying to forecast our uncertainty. And actually, this Paula mentioned that oftentimes we don't have complete statistics about a system, and that's actually the origin of this work. I started a project about 12 years ago with Paul Losowitz and Mike Weir. They gave me a stack of 50 articles, one of which was titled On Incomplete Statistics. And that led us to developing a program where we were going to try to apply tools from complex systems and information theory to, in that case, detecting complex signals. And what I'm going to apply it to here is how you do assessment when you are trying to forecast uncertainty. And at the heart of it is a very basic question that is also very counterintuitive, and it is in some sense the origin of information theory, but the way it's taught actually doesn't lead to a simple understanding of it. So part of my goals in my research have been to bring ideas from complex systems and information theory and apply them, but also to frame them in a much simpler way to understand. So before I start my talk, I want you to think about how you would assess the average uncertainty when you have a distribution. And just as a toy for context, an example might be that you know that a system is under attack, and you've identified different phases of the attack, and you have assessed some probabilities of where the attack, what phase the attack is in. We're very used to calculating the mean where, if we had a set of numbers, we would take the probability and multiply by that number to get a mean. But along the y-axis, how would you assess the overall uncertainty of this attack? And before I start my talk, I want you to think about that question. What would be the mean probability? And have an idea in your mind how you would calculate that. And my reason for this is that the answer turns out to be counterintuitive, but quite important in establishing any metrics. So what I'm going to go through is I'm going to go through that question from an information theoretic framework, and then I'm going to use that to design ways that we can assess our performance in making forecasts about threats. And then once we've done that, I'm going to show you a tool that we've developed that we call the risk profile, which incorporates ideas from complex systems about how you would put valuation on information, and in particularly how you would value risk. And then I'll conclude with some suggestions on how this can be applied. So I want to go through sort of the natural things that people do all the time in the way they average probabilities but turn out to be incorrect. We can't just sum the probabilities and then divide by the number of samples, because then we always, if it's a distribution, this is always going to sum to 1, and that'll just give us the inverse of the number of states. This expression here, where we multiply it by the probability also, is extremely common. I could cite brilliant people in quantum mechanics who use this, but it also turns out to be not accurate. And in particular, what you end up here with is really more like the probability of an event happening twice, and it could be any one of the events. But this turns out not to be the average uncertainty of this situation. So this question, in a sense, is the origin of information theory. And what Shannon and Boltzmann-Gibbs provided was a way to measure the average uncertainty, but what they pointed out is that you have to take the average of the log of the probabilities. And so we're actually translating the scale, and rather than taking the average of the probabilities, we're taking the average of the log of the probabilities. And this at the heart is information theory. But as I've tried to apply this and communicate this, what struck me is that while this gives a correct mathematical answer, you lose all the intuition about how probabilities express uncertainty. So, in this little graph, the darker ones are the original probabilities. And now I'm on a completely different scale that we call entropy. And I do get an average, but I no longer have any intuition about what that number means. So it turns out that missed in the whole revolution on information theory was that Shannon actually taught us a way to calculate the average probability, but we typically don't use this. And I think it's important in our work that we translate back to a probability. And you can do that by any information theoretic function that you use that gives you an entropy can be translated back to a probability by taking the inverse of the log. So you would take the exponential to a negative, the entropy function. And so entropy itself actually gives you an expression for the average uncertainty, but it turns out to be the geometric mean of the probabilities rather than the arithmetic mean. So this expression here is sort of the key one. And I want to get this idea across, is that when we deal with probabilities and uncertainty, we are dealing with a multiplicative scale rather than an arithmetic scale. And so when we want to know the average probability, the approach to that is to multiply all the probabilities together. That gives us kind of a total probability, but then to scale them based on that probability again, and that raising to a power is now our weight of how often that event is occurring. And I'm going to use this, I'm going to go a little bit further. The cross-entropy turns out to be really important in terms of evaluating algorithms, and I'll wait to explain that further because I'm going to use that a little bit. So again, just emphasizing this point that in addition to teaching us about entropy and the length of information, Shannon also taught us the average probability, and most of us aren't aware of it. The average probability is the geometric mean. So again, on our chart here now, if I just plug that in, I get this number here, 0.15. But the point is that I now have my average uncertainty on the same scale as the original numbers I was reporting. So this is a much more intuitive number than the entropy. And we're going to need that because I'm going to actually try to incorporate some much more sophisticated tools into the analysis where the mathematics gets much more complicated, and I won't burden you with much more mathematics. But I needed this because once, and maybe, I guess before I go on here, the point here, each one of these contributes to the uncertainty by the uncertainty of that event raised to the power of how often that event occurs. They both, when you want for a distribution, those numbers are the same, but for other problems, they might be different. So now what I want to do is apply this to how we would assess how good our forecasts are if we're reporting probabilities on a threat. And the key here is that, if the typical process for doing that is that we develop a confusion matrix about how often we reported the correct classification on that threat. Other things are like the receiver operating curve. But these metrics are really evaluating decision boundaries. They're not evaluating the models that went into making that forecast. And it turns out that the accuracy of the process goes into assessing those forecasts is much more difficult. And there's a lot of literature in it. And frankly, a lot of the literature is quite confusing. A lot of it revolves around literature called a proper scoring rule, where essentially the scoring rule is based on entropy as a starting point, but then there's reasons why entropy turned out to be not a great rule, and a lot of other variations were invented. I'm going to try to frame this back in terms of entropy, but then also show how we can modify that for other purposes. And the way I'm going to do this is that I'm actually going to deform the measure of information, and that deformation is going to be a way of me evaluating how much I value that information. And in the sense, this is kind of a new way of measuring risk. In some of the other charts you've seen, risk is typically modeled as kind of a likelihood, how uncertain you are about the event, multiplied by how much you care about that event. And again, that's kind of that in a sense is a multiplicative valuation on risk. It turns out that in human nature and biological systems, we actually put a much more severe cost on risk, where this logarithmic curve, the red one, is the negative logarithm, and that would be the Shannon information theoretic measure of uncertainty. That's our entropy scale. But now, actually, I'm going to deform that and have it go to infinity much faster. And by doing that, I'm going to have like a power law measure of what the effects of risk are going to be on making assessments. At the same time, I can go the other way, and I can actually lower the cost of risk and keep the cost finite when I report a probability of 0 for the true event. This is like what we do when we make a decision. When we have to decide on something, we are incorporating some risk into that decision. And typically, we only put sort of a finite cost on getting that wrong. But now what I end up with is a whole spectrum of curves that will give me a risk profile. And again, not really dwelling on the mathematics, but the origin of this is the Solace entropy generalization of Shannon's work. And now, though, to kind of get this in a more conceptual framework, I'm going to go through this same process where I have what I call now a coupled surprisal, which is this family of curves. I can take the arithmetic mean of those on that scale, and that gives me this generalization of entropy for my measure. But now I'm going to do one more step, and I'm going to translate that back to a probability scale. And it turns out that that function becomes the generalized mean. And, you know, in a sense, my report back to you, Paul, 12 years later about Solace entropy is that at the heart of it is a much simpler concept. All of the work in trying to incorporate complexity into new measures of information can be summarized by the generalized mean. It's an easier function. It's much more intuitive. And from here, we can build our models of risk. And I'm going to show that in the next slide. And so actually, before I go into some examples, so just look at this toy again and what this gives me. So the blue one is the Shannon measure of the average probability, and the red and green one are two samplings from the Solace entropy back on a probability scale. Coupling equal to 1 is my arithmetic average, and in some sense, part of why people still use it is that for many problems it is close enough. And you can get useful information out of the arithmetic average. But we shouldn't rely on that as the true average uncertainty. What it does provide is kind of an upper bound on your uncertainty if all you care about is making a decision. This is kind of where I'm putting a finite cost on my information, and therefore I'm willing to accept some risk. So I actually report a higher probability on the uncertainty than is merited by a true unbiased analysis. On the other hand, because I see this a lot, I feel strongly that A, we need to be moving towards this more accurate measure of information, but we also need to be paying attention to how robust our systems are. And the lower bound is, for mathematical reasons, I'm actually choosing minus 2/3. But that gives me kind of a lower bound on if there were things I wasn't able to model, in a sense, like Laura pointed out in her talk, then I might want to put a higher cost on the information that I have in order to make sure that the system may be robust against things that I wasn't able to test against. And so now what I can do is I can provide a full spectrum of an algorithm's performance against what I call this risk profile. And so again, giving kind of an example of this in a classification problem, and this is just a toy problem, but you could imagine trying to classify different types of threats on a network. In this case, the way this problem is set up is that it's an image processing problem where you're trying to identify 9 handwritten numerals, and you're trying to classify those. And once I have a model of the process, I might make a histogram of what probability I reported for the true numeral. And I might build my algorithm in different ways. And in particular, in this example, we were looking at different types of ways to fuse information together. So I had in this case 6 different features of this image, and I wanted to fuse them in different ways. A common technique is the naive Bayes, where I assume independence, but I don't get accurate probabilities because I have ignored all the correlations. And the result is I report a lot of 1s and a lot of 0s. And the way that translates to my risk profile is that on the decisive side of the metric, I still do very well. For instance, for the arithmetic mean, my probabilities actually look quite good. And in some sense, this is where people get into trouble, because they've measured the classification performance, it's quite good. They've measured the average probabilities using the arithmetic mean, and they think they're fine. But against the Shannon metric, if I use this multiplicative mean, I start to see where the problem is that while I've classified well, I have not forecasted my uncertainty well. And there's a big difference. So now some other solutions, a solution that turns out to have the opposite problem is just to average the probabilities from these different features. And here, I get a lot of robustness. You know, I'm very conservative in the way I'm forecasting uncertainty. But I'm not able to make decisions easily because on the decision side of this, I don't have any separation here about the uncertainty. And in this particular, and again, sort of emphasizing this point, the log average turns out to be a very good model. And they're related. This is not disconnected because the log average is also equivalent to the geometric mean of the probabilities. And if I don't have any better model, or if I don't have a good model of the correlations, and we want to fuse information together, we should always start with the geometric mean of the probabilities as a starting point. And it comes from information theory. It comes from Shannon's work on what the average probability is. So again, another sort of take-home point, if you're uncertain, if you're trying to fuse a lot of information and you're uncertain about the correlations, always start with the geometric mean as a starting point. But we can go a little bit further here, and something we've done at Raytheon is we've designed a system where rather than reporting one probability, you actually report 3 probabilities. And those probabilities are optimized for different purposes. One is the decisive metric, and this, in a sense, to me, is sort of the current state of the art, the way most sensor systems are currently designed, because they're not actually doing this kind of testing. And then secondly, we designed the algorithm to report an accurate probability based on neutral bias of the risk using the Shannon metric. And then a third one was biased to be robust. And so now my output reports 3 probabilities, and the green ones you can see in classifying this, the classification is pretty good, and the green ones are all close to 1 with a few exceptions. But the problem is the exceptions don't really give you a measure of how uncertain you were. And so now with the red ones here, you can kind of flag some of these samples where there was actually higher uncertainty. And in particular, where this becomes important is that if I know I'm uncertain, that gives me a flag to try to measure more information about that particular sample. And I think with that, I'll try to just wrap up, because I know we'd all prefer to eat lunch. I have a few more examples here, but that's really the heart of the talk. So my takeaway for the cyber community in designing better metrics is that there are things about information theory that are kind of counterintuitive. And the whole purpose of taking the log of the probabilities was to be able to do the typical kind of arithmetic analysis that we're all used to, like taking the arithmetic mean. While those are important, and that's certainly a good way to do analysis, I think we really owe it to people that aren't as familiar with the mathematics to translate our work back to probabilities. And when we do that, the average uncertainty is the geometric mean. That's really my important take-home message. And then from there, it turns out that some of the latest advances in information theory actually can be incorporated in a fairly intuitive and simple way that it turns out the generalized mean gives you a whole spectrum of what an algorithm's performance is. And I like to think of this as sort of being, what is your tolerance for risk? If you know that you need to be very tolerant against risk, then you need to use the robust metrics. If you're kind of neutral to risk, but you want the probabilities to be accurate, then you need to follow Shannon's work. And the problem I see is that all of the current methods really are designed to measure whether you made the right decision or not. That's important, but in doing so, we are building systems that are not robust, that turn out to be brittle. So I can take questions at that point. Yeah, go ahead.
So how could we use this and put it into something like what SCR, what you presented? How can we merge that together? What's the future of that?
Yeah, so what I see is that in a lot of the different categories that SRC was applying, within those are probabilities. And what I'm saying is that you have to be careful about how you do analysis on those probabilities in order to really get the truth back in terms of how well the system is working. Yeah, so I think that is an important discussion to have. Others?
One quick question. It seems to me that this is slanted toward reduction of false positives.
Yes, it is, but in a little bit different sense is that even the receiver operating curves, are kind of oriented towards whether you made the right decision or not. right? So reducing false alarms, right? That's kind of the first step. But the other really important thing is, did I make a forecast that was accurate about my uncertainty? And that's critical because in a live situation, if I have an accurate forecast, then I may have opportunities to delay a decision and gather more information before I make that hard call. Once I've made the hard call, oftentimes I don't have opportunities to go back.